Oh, fun fact, if you're curious, the first day of autumn is in 3 days. So I guess the weather out there is probably appropriate. Welcome back, everyone. For today's class, our whole objective is to practice differentiation on functions that came as a result of a function composition. So we're going to see how to unwind the derivative of f of g of x written in this form, or indicated this way where we have to use a formula. And that's the whole purpose of the chain rule. The chain rule is probably one of the bigger formulas that we're going to see that has loads and loads of ramifications. If you see, for example, a function that looks like this, y equals e to the x, and it's really not a big deal to work with that thing. You differentiate it and you get y prime is itself. So the reason you might need a chain rule is anytime you see something that looks like this, what if your function is y equals e to the power of cosine of x? Now we have a problem, right? Someone put a cosine function, that's like the g right here, the inner function, inside your exponential function base c, that's like the f function here, the outer one. No rule that we have so far tells us how to differentiate this at all. It's kind of remarkable. And there's loads of functions that you can combine in strange ways like that. But if you don't have the chain rule as part of your repertoire, a vast world of functions are completely undifferentiable because we have to know how to untangle a composition first to work with it. So that's the major goal for today's work. After that, we'll take on implicit differentiation, section 3.5. But any questions at the moment, folks, before we get started? Okay, only quick reminder I have is our assignment number 4, which was intentionally a small section after our exam. This one's due tomorrow, just those sections here with product rule and quotient rule. So now to start off in the chain rule, oh, I forgot to open the notes. Let's first do that. On the organization of these notes, I have the chain rule stated twice. Here, I'm going to focus primarily on the Leibniz notation on example 1, and it's really just kind of a warm-up example. Then on the second example below, we'll focus on the chain rule written in this form using Newton's prime notation here. For the kind of problems that we solve in Calculus 1, we're typically going to be thinking of it in these terms, but it's always a good idea to pay attention to Leibniz notation, so we'll start right there. So here's the idea. It says if you have a differentiable function g at x, so here it is, g of x, that's a differentiable function, but if f is also differentiable at g of x itself, the composition going this way, f of g, redefined in this way, is also differentiable, and it's given in this way. The derivative of f at x, well, first let's organize this really carefully. There's two functions here that we want to differentiate on this line where we see an f of x. We're going to be calling it f prime at x. And the first thing that happens is we differentiate this first, the f function. We're going to call it the outer function. The reason it's the outer function is the function g of x, which we differentiate on the second run or the second step, is our inner function going inside. So I'll put here a 2 to say that that is the inner function. Then if we take a look at, let's say here, let's take a look at the Leibniz notation. That's one we're going to handle first. If y is equal to f of u, here's our first one right here. We differentiate dy du. And if you let u, a new variable, stand for g of x, then that's the second thing you differentiate. And you multiply together in that kind of way. So if y is this overall composition, f of u, where u is that g of x function, your result of differentiating f would look exactly like this. Let's just put a quick note here to tie the ideas together. This is f prime at x. Any questions about that so far? Okay, the example 1 I have here is a very silly example. Its whole purpose is to make this seem plausible. The idea is that rates will multiply in the right kind of situation. So here's our example to start this off. It says here, a car goes twice as fast as a person on a bike. It's probably an old car or something like that. If we write this in Leibniz notation, this is the real deal. The rate of change of the speed of the car with respect to the bike is 2, since the car goes twice as fast. So that will be our first derivative that we'll track in the chain rule. But now it says a person on a bike goes 3 times as fast as a person on foot. Probably not a very good bike. It seems like it could go a little bit faster. But just like before, likewise, in Leibniz notation, the rate of change with respect to the bike with respect to being on foot is 3, because we're going 3 times as fast. That takes us to the overall question. How much faster is the person in a car than the person on foot? That's kind of weird because, well, we know how the car relates to the bike, and we know how the bike relates to the person on foot, but they're asking us to go from the car to the foot. We can absolutely do that. And any volunteers for a number of what that ought to be? Ought to be 6, absolutely. So that's why it's kind of a silly problem. I mean, we don't necessarily need calculus for this, right? We're just trying to see, how does the chain rule come together in this picture? And so when we put this together, here's what it looks like. I'll scroll just a bit so we can focus on this line right here. So the rate of change of the person in the car with respect to the person on foot. In Leibniz notation, well, we know we're going to be using the chain rule because we're relating car to being on foot, but there's no such derivative here. So we first put in the rate of change of the person on car with respect to the person on the bike. That's the first portion right here of the chain rule in Leibniz form. And then it multiplies by the rate of change of the person on the bike with the rate of change of the person on foot. So that right there is how the chain rule comes together. And this is a little bit tricky in Leibniz notation because the temptation is to think of Leibniz notation as a real honest to goodness fraction. But sadly, it really isn't. If you see dy dx, recall that that's the limit as h goes to 0 of f of x plus h minus f of x divided by h. So these aren't really honest fractions, but if you think in terms of analogies, and you were to cancel in that way, it brings back the left-hand side. That's purely just an analogy to let you know you put together the chain rule correctly in its Leibniz form. Then after we do that, we can go and make some substitutions. For this first derivative here, d car d bike, we have a value of 2. And for the second factor, d bike d foot, we had a factor of 3. And so that's our initial guess from the class. The rate should be 6. The person in the car should be going 6 times as the person on foot, provided this information right here. Kind of strange information, honestly. But again, that's essentially what the chain rule is trying to do. Our functions are really tangled in a certain way, and Leibniz notation or Newton prime notation, the chain rule untangles it and gives you back the derivative you're trying to find. Well, any questions at all, folks, with this problem here? Okay, again, think of example 1. This one's really just a warm-up. A more typical example, like would be in a homework problem, could be example 2 or example 3 we're going to work on next after this one. So the purpose of example 2 is focusing on the same rule, chain rule, if you did it in Newton's prime notation with what's highlighted here. Same kind of idea. If we have a function here and a function here, notice we copy g of x right there. Probably, yeah, we can leave it like that. We do put it down here, but we differentiate it. And over here, we're differentiating f in that location as well. So here's a function, f of x equals f of g of x. We also have information about that function. And our whole goal is to evaluate f prime at 0. It's another strange question, just like the car, bike, and foot question we just looked at, because we have no clue what f and g are as functions. All we know is differentiable at the values in question, and we want to find that derivative there. First thing I would do is, let me just copy f of x is f of g of x. And this segment right here could have just been rephrased in this way. F of g like that expands to this once we write out as a formula. So if that's our function, here's what essentially happens. F prime at x, the first thing I'll always do on these notes, just to train our eyes to get a feel for the chain rule, is identify which function is inner and which function is outer. It actually helps out a tremendous amount. So if the chain rule has kind of been a bother when you go to do this homework, come back to these notes and try out this strategy. It could be a big help. So here's what I would always do. This function right here, g of x, we'll call this one the inner function. And this function f right here, we'll call it the outer function like before. Now, like I did in the top of the notes, I put a 1 here because that's the one I'll differentiate first. And I'll put a 2 here just to indicate this is the one I'll differentiate second after a little bit of space. So what I mean by that is whatever the function f is, it could be a square root function, a power 3 function, the cubic function, or maybe a cosine function, you differentiate that immediately. So here we go, f prime times something prime. So that's how it goes on the very first step. I differentiated f, I put in a little blank here, then I produced another blank with a prime symbol. That's what's going to go inside there. So when we say we differentiate g second, it's because it goes into this location, g of x. And that location, because of the all-important Newton's prime symbol, this one we take the derivative of, but over here, we just copy it in. Notice there's no prime on that g of x, it just goes directly inside. So your inner function goes inside the derivative of the outer function, and then we multiply by the derivative of the inner function. That's essentially exactly what was happening right here. It just is disguised a lot because Leibniz notation looks different. So there it is. Now, if that's f prime at x, that doesn't answer the question. We need to find f prime at 0. So this is where the problem, to me, gets a little bit tricky. There's a lot to look up. F prime at 0 will be f prime at g at 0. All I'm doing is putting a 0 in for x into all of these locations times g prime at 0. So let's start filling in this information. When it says g of 0, that's going to be this portion. Only because there's no prime symbol on that. So we'll have f prime. Right where the red dot is, I'm going to substitute the value 8 for the g prime at 0. Or excuse me, for the g of 0, which is what was inside. Next, g prime at 0. Let me highlight this one right here. We're just throwing in a 4. So there it is, times 4. Does that make sense so far, folks, on evaluating the derivative at this stage? Awesome. So we've used up this, g of 0 is 8. We've used up this, g prime at 0 is 4. And now, notice they gave us a value, f of 0 is 3. I mean, it might be true, it's their function and they said it, but this actually doesn't come into play at all. We didn't need it. The one we needed is this one, f prime at 8, because that's what emerges right here. Honestly, that's kind of rude. I would never write an exam question that way, but that's fair game from homework because the objective of a homework question is for us to know which information is needed and which information is extraneous that we have to disregard to solve the problem. So we'll put in a -2 right in that location. So this becomes -2 times 4 for a value of -8 altogether. Now we've done it, folks. Essentially, all I've done is recopy the function. This right here is the chain rule right at the red dot. And this is just something extra, doing the evaluation according to all this given information. Any questions at all, folks, on getting through this portion here? Okay. And again, this is the big takeaway. This was the chain rule right here. So what we ought to do next, just immediately, is let's practice doing this kind of stuff and see what we get for problems where we actually have a formula for the function. Any questions at all before we go to try example 3? Okay, I'm going to copy, for the sake of quick reference while we do this portion right here. So the derivatives we'll try out. Let's kind of warm up first and do a part A and a part B all at once. Well, maybe not all at once, but we'll compare them as we go. So my part A is going to be the function that goes y equals cosine cubed of x. And my part B is going to be the function that goes y equals cosine of x cubed. So I put parentheses in on this one, mostly because that's my style for writing this kind of thing. But if it was in the textbook, it would have looked like this instead. I'm going to drop the parentheses just to make it more familiar with what the problem would look like in a textbook. And what's really tricky about these two problems right here is, yeah, we got to use the chain rule, but if we can't see which function is inner and which function is outer, then we're kind of stuck on the chain rule. It's a pot shot. We're pretty much guessing. Here's the second problem. That notation right there is also really, really tricky. It's helpful in certain ways and tricky in others. This is a tricky situation. In fact, I would say that's the easier function to differentiate rather than part A. But let's stick with part A and see what happens. First thing we'll do, we've used this trick before, is write, I'll go to a slightly different color, y equals cosine of x to the power 3. If we write it this way, we're just saying more exactly what does it mean to have a power 3 there. That means the cosine function is being cubed, but in this format, it's also a little bit easier to tell which function is the inner function and which one is the outer. Any volunteers for which should be inner? Is it cosine or the power 3? It would be the cosine function, absolutely. If you were doing order of operations and your value x was, say, pi, the first thing you would have to do if that was pi is calculate cosine pi. Because cosine is the first function that comes up in order of operations, that's a reason you would call this the inner function. That means we'll handle that one second. And this, the power 3 function, is the outer one. It's just like y equals x cubed, except the x is cosine x instead. A little bit annoying, but we can definitely navigate that. So next step is we're going to run through the chain rule in this format. You know, I honestly wish I changed my color coding. Let me put here cosine x on this one. And I guess blue here works for that outer function. We can now write dy dx for the derivative is going to be equal to, and I dropped something here. I want to put a 1 on that just to say, do that one first. Okay, now we're ready to begin. We know what's what. We take the derivative of the outer function. Because it's a cubing function, here's what happens. 3 comes down, and the new power is 2. Does that make sense to visualize what happened to that cubing though? Awesome. The analogy here, I'm going to delete this in a moment, but the analogy is, it's like we're thinking of y equals x cubed. So y prime would be 3, x to the power 2. But I put a big blank in place of where x was, an open parenthesis, because it's not x going inside, it's cosine x instead. So next thing I would do is say times the derivative of something. That prime symbol I put right here is matching up with this prime symbol in the chain rule formula. And every time I do the chain rule, especially if I'm practicing it, this is always my step 1, or I guess it's kind of a step 2. My first step is really analyzing outer and inner function. Then when you differentiate, leave these open parentheses, and it really helps the eye to show what goes inside. Cosine x here, cosine x here. Notice you're copying both times, but on this one, there's a further step. That one we have to take the derivative of. But we're getting there, folks. One more step to go on this one. Any questions at all on this stage right here? Okay, when we go to crank out this derivative, it's going to turn into 3. You could leave it cosine x, then power 2 with parentheses like we have, or you can go back to a more compact notation, cosine squared x. It's all a matter of preference. It's a stylistic choice, so whichever way is more comfortable to you. But it would really help me if I make that 2 look like a 2. There we go. So that portion's done. Next, we differentiate that cosine x, and we recall what derivative of cosine should become. Good call. We have negative because it's a cofunction, and then sine. So that's pretty much it, folks. We did it. The answer is 3 cosine squared x times a negative sine x. Those parentheses around negative sine x are absolutely required because we're multiplying things throughout. But you could be a little bit more compact with this and call it negative 3 cosine squared x sine x. They're both just fine as answers. I like this one better because it's less easy for me to miscommunicate subtraction versus this right here. It's easy to get a miscommunication on that answer. Well, that's the first one done. We get negative 3 cosine squared sine because the function went like this. But now if we change it up to this, everything is different all of a sudden. This time, x cubed. This one's going to be considered the inner function. And cosine, this one will be the outer function. So let's give this one a try next. We'll go dy dx. Because the power 3 is way out here, it's automatically assuming what's being cubed is x, not cosine. So it's almost kind of nasty, right? The 3 right here by the cosine means you're cubing your cosine function. Over here, one tiny little change of position, now you're cubing x, and it's an ordinary power 1 on cosine. But let's go through the process. First thing you do is you differentiate the outer function. Cosine goes to a negative sign, so I'll write it like this. Negative sine, put a big parenthesis in it as a placeholder, then multiply another parenthesis with a prime symbol, just to remind yourself you're differentiating right here. Then, anyone see what should go into both of those open parentheses? Exactly, our inner function goes inside both. So that's pretty much the tricks to getting through this. I'd say the hardest part about this is not necessarily this line where we're writing out the chain rule. It's more this when we're analyzing which function is inner, which function is outer. Once again, you can always think of, pick a number for x. Maybe it's 2. If you plug 2 inside here, the calculator is not going to take cosine 2. It's going to take cosine of 8. Because the first thing that happens is you cube your 2, and that's what's making it an inner function. So if you think in terms of order of operations, sometimes that's a great way to tell which is which in the lineup of functions. But now finally over here, we have one last derivative to go. This is negative sine x cubed. Here we're still differentiating. Derivative of x cubed becomes times 3 x squared. And I'm completely fine with that as an answer. Usually I have a need to rewrite it as negative 3 x squared sine x cubed, like this. And even I would drop the parentheses because now there's no miscommunication that the 3x squared is not going inside the sign. But no harm in putting the parenthesis in, even right there, if you want to be very specific. So on one hand, we differentiated, got to negative 3 cosine squared sine x. But on this hand, we got to negative 3x squared sine x cubed. Entirely different result because the functions themselves are entirely different. But again, that's the kind of danger with these problems. If we can't separate out what's inner and outer, maybe there's something weird like a trig function going on. All this work suddenly becomes kind of weird and mysterious. If you go solving these problems in homework, you're always welcome to send me a question and say, hey, Mike, how do I start this one? Which is the inner function? Which is the outer function? I'll always be very happy to help out with that if you get stuck on any of these. Well, that's 2 derivatives down. Any questions at all, folks, on getting through them? Okay, my goal today is mainly to practice more of this kind of stuff because we'll use a chain rule essentially all of the time in a calculus 1, 2, or 3 class. So let's give this some more practice. So that's parts A and B. Now let's turn to part C. On part C, it's nothing too wild, and it's kind of a nice function to start off. F of x equals a base e exponential to the power of x squared minus x. So that's the original question. I'm just going to copy it down so we can start color coding it. So there's a lot of stuff going on here, but there's really two functions. There's an inner and an outer. Anyone spot an inner function on this one? Good call. It's going to be that entire exponent, like you said, x squared minus x. So that's our second portion, the inner. That's kind of unfortunate. It's usually easier to spot the inner function, but it's the thing that you do second as far as the derivatives go. So it's the first thing I spot, but I need to remember to put a 2 instead of a 1. That means this function, essentially e to the x, that's the inner function. Excuse me, the outer function we do first. So now we're in good shape. The derivative would be written this way, f prime at x, or df dx if you prefer Leibniz. But one of the two are just meant to help us to do this in order. So first thing we do is differentiate the base e exponential. Its derivative is itself, but we're not going to write e to the x. Everywhere you would have put an x, put in a huge blank with parentheses. E to the something, then it's going to be multiplied by the derivative of something. I'll use black for this, I think that'll show up better. So if you've taken the derivative of the outer function, essentially, put the parenthesis here for x, this thing in black is just part of the chain rule. We are going to multiply by the derivative of what's inner. X squared minus x would go here. And then we also put it here, copying it into two locations. Even though we copied twice, this one has the further step of differentiate at that level right there. But we did it, folks. That's the major setup of a chain rule. If this was a 5-point question, I would consider this much 4 out of 5 points. Even if I made a mistake and just flubbed it on that derivative, you've got most of the credit, since this definitely shows understanding of the chain rule to that stage. Well, last thing we have to do is differentiate x squared minus x. So this turns into e to the power of, we can drop those parentheses, or mostly for organization. X squared minus x is its power. These parentheses we must keep because this derivative goes 2x minus 1 containing 2 terms. So that's the derivative on this thing. Essentially, derivative of e goes right here. Copy the input x squared minus x and multiply it by the derivative of that input. Essentially, that's how our chain rule goes each and every time. Any questions at all, folks, on this one here? Okay, does it make sense on how these break down at the moment? Awesome, glad to hear that. Let's try one that is, let's see, not too bad just yet, but it's kind of building towards something. Let's let part D be g of x equals another exponential, but this time it's annoying. It's a base 5 exponential because why not? We can definitely do that. And the exponent, instead of an x squared minus x, let's do x tangent x. So that's a wild function, right? It's a base 5 exponential with a interesting exponent in its own right. We want to differentiate that. We'll first hide the application at the very bottom. There we go. First thing we have to decide is which function is inner. Well, it kind of goes like this one did, right? The whole exponent itself is what's the inner function, x tangent x. So let me actually do one extra step on here. I like to get in the habit when I write these notes in writing down the problem twice. That way, if you come back to the notes, right here is the original question, and everything below, once we start highlighting, that's going to be our solution. So that right there is the inner function. So we'll label that with a 2. Base 5 exponential, we'll label with a 1 since it's the outer function. And I feel like for this problem, I personally would want to refresh myself on this derivative because that's not a derivative we do a lot, right? It's usually an e to the x. So this is a good formula to have at the ready. If y is equal to a base a exponential, so a is any number that would make sense as an exponential function. It has to be positive, it's not equal to 1. And we have it raised to a power of, let's just say, x. Then y prime would be a to the x multiplied by something. Good call. I was about to ask, anyone recall? To me, that's one that's really hard to remember, but it'd be the natural log of a once again. Good call. So if we have that thing as our outer function, we're going to be using this formula to crank out its derivative. Any questions at the moment before we go through it? Okay, let's give this a try. So the function g is a result of a composition. So when we go to do g prime at x, here's how the chain rule will go. I'm going to take the derivative of the base 5 exponential. It'll look like this: 5 to the blank, big parenthesis, times a natural log of 5. So 5, here's our parenthesis, natural log 5. Then the chain rule says multiply that by the derivative of something. Once you have this portion down, it's also a lot like product rule or quotient rule. It's all about putting the right things in the right locations. And if you have the outer function fully differentiated, x tangent x just goes into all of those open positions. So here as an exponent, and here where we have to differentiate it. Power rules say we're at. Yes, exactly. But aside from, I think you're meaning product rule. Yeah, exactly. We have to use now the product rule on this one. And this is again in the way, and the problems start to get a little bit tricky. Every rule that we come across can now mesh together with every other rule. In fact, we've been doing that on this one. We had to use the sum rule right here when we differentiated. So we took the derivative of x squared, here's the 2x, copy a minus, derivative of x turned into 1. Here, well, same kind of thing in spirit, it's just that that one's a product rule and it takes a lot more steps. So we'll go through that one as a whole another problem inside the problem. Other questions at the moment before we start? Okay, to me, this is when chain rule starts to get tricky, when all the formulas are coming together. So I'm going to put just a note here that all of a sudden we have a product rule. There's a couple strategies. If that's our product rule, you can keep on copying this line down as if you solve it with the product rule, or you can work in the margin and just take the derivative, say, let me get a different color. I'll do it down here. Actually, green's just fine. So for the product rule portion, we're going to take the derivative of, let's see, I'll put it maybe over here. X tangent x, that's not quite going to fit. I'll put it maybe down below. X tangent x prime. So that's the derivative we're doing here. Because it's a product rule, we'll begin with 4 parentheses, 2 pairs of which are multiplied, separated across addition. And that's essentially the start of every product rule. Unless you feel like you've done this enough, you just want to write down the answer as you see it, that's always completely fine as well. So this breaks up as x. Oh, first thing I should do is never forget your derivative signs. I mean, as long as you differentiate, I'll be happy, but it's considered a bad idea to forget to put these in. If you read your work, it will suddenly make no sense if you're not saying where you're differentiating. So with that correction there, let's put in x into the first spots, tangent x into the second positions. And now we're ready to find the full-on derivative of this whole mess right here. Derivative of x turns into a 1, so it's just 1 times tangent of x. Plus, over here we copy in x, and derivative of tangent, well, this one turns into a secant power 2. So secant squared of x. And that does it, folks. That's the whole result of the product rule. Any questions so far to that stage? Okay, so essentially all I've done is taken these 2 derivatives, copy the result down in the further line. But all of this is going right there. So that's going to be our next step. I'll delete the arrow so the paper doesn't look crazy. I'll put a little border here just to say that is part of our solution, but I don't want it to interfere with the last line. And finally, here's our answer. The derivative of g at x is 5 to the power of x tangent x, multiplying natural log 5, and now multiplying this whole function right here, derivative of x tangent x. We'll need parentheses because of the addition. It turned into tangent x plus x secant squared x. I'm going to box this one out because I have work above and below, but that box is the end of result for our problem. Any questions at all, folks, on running through this result here? Okay, they sometimes get long, and that's kind of the punchline on part D. This is one of those longer ones. Other times, the chain rule can be hard because the algebra can just get out of control. Or another way, there could be more than 2 functions in the chain. How about a higher chain rule? Does that sound all right to folks? Okay, we might have something with 3 functions. It could be a composition with 4, 5, 12 functions, but the chain rule really doesn't actually care. It goes in the same exact way. So let me show you how a multi-stage kind of problem would go along these lines. I'm losing the parts here. This looks like part E so far. For part E, let's let the function be y equals sine of the square root of x squared. Oh, geez. Sorry, must have clicked on something weird. X squared plus 1. So that's our function. Now, when we look at this, there is one big annoyance, and this isn't even chain rule or composition matters. If we're going to differentiate all that, you probably wouldn't want that square root symbol because it's hiding what the real exponent is, power 1/2. So what I'm going to do is rewrite the function on our solution below as y equals sine of, let's put in a bracket to make it more readable, then a parenthesis with power 1/2, close a bracket, and inside that parenthesis is x squared plus 1. Well, I think we're ready to go. Now there's 3 different functions. Color coding starts to break down at this stage, but that's okay. The sine function is the outermost function. There's a middle function. Anyone spot what it would be? Exactly. Square rooting power 1/2 function is our middle. We'll do second. And now the inner function is just the x squared plus 1 right here. So there's 2 kinds of ways to do this. If you felt like you're really getting fluid with the chain rule, sometimes people write the answer to this all at once. I want to show you how that goes, and then on a second method, a step-by-step process. So let me know which one you might like better. And let's call this method 1. So the end goal of the chain rule is to kind of work it out in this kind of way. If that's y, I'll call it dy dx, since we're taking the derivative. And this is the process I'm going to take. Differentiate sine to start. We get a cosine. I'll carry in the bracket. And everything goes inside that cosine function that's to the right of that bracket. So x squared plus 1 to the power 1/2 would go inside there. Now we go to 2, and we have to differentiate this function right here, the power 1/2, or the square rooting function. So what happens is 1/2 will come down. The new power is going to be 1/2 minus 1, so that'll be negative 1/2. And we put inside there the x squared plus 1, the innermost function. Then we multiply that by the last derivative, the derivative of the inner function. Well, derivative of x squared plus 1 just turns into a 2x. And that actually is the right answer. We do have some simplifications we have to make here. For example, this 2 cancels with this 2. If you wanted, you could convert this to a positive 1/2, throwing it into the denominator, producing a square root. The back of the book does that quite often, but that's really a stylistic choice. If you write your answer in this form, cosine x squared plus 1, I'll say square rooted just because it looks nicer, easy to write, times x squared plus 1 to the power of negative 1/2. times x, then that's the right answer for this process. But it's kind of tough to do it this way. It's valuable when you have three functions all in one composition because it could take a lot of steps otherwise. But let's try method 2 just to see how it could go if we did break it down a little bit more. Before we try method 2, any questions at all, folks, on getting through it this way? Okay, so I'm going to copy the function again. Now let's call this method 2. That's probably way too big. So with method 2, pretty much all we're trying to do is solve it in the same kind of way that we were solving all the rest of the problems. This may not be enough space here. Let's go to a second page. The start would be first write dy dx. I will differentiate the sine function to start out. That will turn into cosine just like before. So we have cosine of something multiplying by the derivative of that thing. So what would go in both parentheses is everything inside here. The middle and the inner function all together would go into those two blank locations. Yeah, go ahead. What do you mean by the composition of middle and inner?
So like taking the 1/2 x squared plus 1 to the power of -1/2 times x to the derivative of x squared plus 1 and then multiplying all of that.
By the derivative of, say, sine? Absolutely. And that's essentially what we did right here in method 1. We took the derivative of all this, or an ordinary chain rule. We give you that as a result right here. Then we just multiply it by derivative of sine with that same stuff inside of it. So yeah, absolutely. If you're thinking in those terms, then that's kind of the faster process of getting through it. Other questions so far? Okay, it is kind of tough sometimes to see it this way, especially if you only looked at the chain rule for the very first time. And that's the only purpose of method 2. Sometimes it's just valuable to break it down a little bit more on a step-by-step basis, like we're about to do down here. So we took the derivative of sine first, and then we just stopped. But this is always the result of the chain rule. We take the inner components, the middle and the inner, which is x squared plus 1 to the power 1/2. Copies there, we don't do anything to it. But over here, we will differentiate it. X squared plus 1 to the power 1/2. But when we go to do this derivative, notice that there's something else that's happening. Power 1/2 is now the new outer function, and x squared plus 1 is now the new inner function in this last location where we're still differentiating. So we'll go through the same kind of process just like before, but imagine everything on the left, we're just copying down. On the right, it's just a brand new chain rule. And if there was more functions inside here, we would just keep on chaining more and more derivatives until we got to the end result. So the next step, it's cosine. I'll convert this to a square root. It's just slightly easier to write. Now over here, we take the derivative of the power 1/2 function, so times 1/2. Throw in a parenthesis, and by that red dot, just subtract 1. So 1/2 minus 2/2 gives us negative 1/2. Then like before, we multiply by the derivative of whatever your inner function happened to be. So there's our setup. X squared plus 1 goes in those two remaining locations. And at this stage, this is the last thing to do. We have to take that derivative right there. It's no longer a chain rule because that's an x squared. It's not like a cosine squared, which would force a chain rule. This whole thing just turns into a 2x. And so our end result becomes cosine root x squared plus 1 times 1/2 times x squared plus 1 to the power of negative 1/2 times, here's the last thing. Now it's not copying, that derivative turns into a 2x like before. Then we get our same kind of cancellation. And here's our end result. We have now cosine x squared plus 1. If you want to change this around, you can make the root or the -1/2 positive by dropping it down below. That would turn it into a square root if you wanted to. So root x squared plus 1 could go here. But I want to emphasize, you never have to do that. I'm okay with the negative exponent. That's more of a stylistic choice right at that position there. Last thing is the x, so I'll just put it right here. So we did it, folks. That's two different methods of getting through the same problem. And I'll leave it up to the class. Which one would you say is more preferable? Breaking it down level by level this way, or just running through it? Kind of hard to tell. I mean, this is the first time we saw chain rule, so we'll probably have a better answer for that after we've done this a bunch of times. Well, with what I want to do with the rest of our time is, I have a couple more problems I did want to get through that are going to help out with the homework. If we have time and we're willing, here's an interesting application immediately for getting through the chain rule in an applied setting. This one has to do with blood flow and how fast blood will flow if your artery is constricting and your blood platelet is a certain distance r away from the boundary of that blood vessel. So that's an immediate application of chain rule, but it's a tricky one. So first, before we think about this one, let's try a couple more problems along these lines. This next one I brought to class because it's similar to a homework problem that's assigned, and I completely forget which part we're on. This is part F. I guess we are going to run out of the alphabet after a certain point. It starts to lose its meaning. But for part F, the function is S equals r squared minus 3 divided by r squared plus 3 to the power of 6. So it's already a weird question, right? It has strange variables. The dependent variable is s. Our goal is to try to not let it look like the number 5. And the independent variable is r. But there's a bigger problem. This one isn't necessarily the chain rule. You could, if you had all the time in the world, just expand r squared minus 3 to the power 6. You'll get a big old polynomial, and that would work. You could do the same to the denominator, and the whole thing would just be a quotient rule. But that power 6 is too much for us to work with. So instead, we're going to think in terms of that being an entire function, and this being an entire other function altogether. So the function that's inner is going to be the fraction, the rational function. The outer function is now the power 6 function. So if we go to differentiate this thing, here's how this one breaks down. You could call it s prime at r if you like. If you're a fan of Leibniz notation, this would look like this, ds dr. And you don't have to write it twice. I just put it on the paper twice just to, again, get us used to saying Leibniz as opposed to Newton's prime. But either way we do it, first thing we do is differentiate this. It's just like if you're doing x to the power 6. 6 comes down. In place of what would be x, we put a parenthesis, and the new power is 5. Then we multiply that whole thing by another derivative. Then the guts, the inner function, copies in both of these locations. So r squared minus 3 here, and r squared plus 3 right here. Once again, r squared minus 3 divided by r squared plus 3. And we're well on our way, right? Except this one is kind of a nasty one, right? Anyone see what makes this problem more nasty than the others? Exactly. Much like the problem that had a product rule that was snuck in, this suddenly requires quotient rule to get through. We can't just differentiate the numerator to get 2r, differentiate the denominator to get 2r, canceling to get a 1. This derivative is not 1 at all. So just a warning on this one. Because of the fraction bar right here, and the fact that we're differentiating with that prime symbol, we'll get a quotient rule out of this. Since it's a quotient rule, I'll break it down like this. Green for the top function, blue for the bottom function. Now let's start cranking it out. There's always two strategies here. If this happens, you could go to a lower section or the margin of your paper, show the quotient rule steps there. Or let's do it slightly different this time. I'll show it all just in line. We'll carry everything down and work through the quotient rule as we go. You don't have to use my strategy if you don't like it. So S prime at R is going to be, so far, I'm going to break this down just a little bit because this is going to simplify in a weird way. I'm going to take 6 times r squared minus 3 to power 5 divide by r squared plus 3 to the power 5. So all I've done is I've raised the numerator denominator to the 5th power and then just multiplied 6 into the numerator like that. Then this is where all the action's happening over here on the right. So let's set up our quotient rule. Let me highlight the portions that are, for me, the easiest parts to forget. It's a minus right there because it's a quotient. And we'll be dividing by the denominator squared in that location. And what the heck, don't forget to put a prime here and here. So next, the function that's on the top goes into just 2 positions, r squared minus 3 here and here. Then all the remaining positions is the bottom function, r squared plus 3. One last spot, r squared plus 3. And that's our full setup for a quotient rule on this thing. All we need to do is calculate this derivative, and then most of the work right after that is just algebra, trying to simplify what we've got. If this was a real exam problem, we would have to simplify it, but I give most of the points for the calculus steps, and usually like 1 point for the algebraic step in this type of problem. Well, any questions, folks, before we run through quotient rule on this one? Okay, so let's say here, S prime of R is going to be equal to, I'm copying 6, r squared minus 3 to the 5th power, r squared plus 3 to the 5th power. So multiplying this new fraction, probably we don't need as long of a fraction bar. This will turn into a 2r in this position. And let me put this slightly different color just to show where this came from. Then over here, we're just copying r squared plus 3. Copy the minus, copy the r squared minus 3. And this derivative, same as before, we get a 2r once again. So times 2r. Down below, it's r squared plus 3 to the power 2. And this is the reason why I split up the powers on this original big fraction here. In that denominator, there is a simplification. We'll combine the base of r squared plus 3 and raise it to the power 7 on our next step. So we're getting through it. And on our next step, first let's do the denominator since it's kind of more interesting looking. I'm combining these two together. So it's going to be r squared plus 3 to the power of now a 7. Over here, I'm just going to copy 6, r squared minus 3 to power 5. I'll put a bracket, and I'm copying all this stuff from the second fraction's numerator. I'm just putting in a bracket to show where all of this stuff is going to come in. Let's distribute in a 2r to get 2r cubed plus 6r. Over here, this distribution always looks kind of funky, but this is how I'm visualizing it typically. I'm distributing in a negative from the left and a 2r from the right. Officially, you're distributing in a negative 2r, really. And so what you'll get on that first distribution is negative 2r cubed. Does that make sense in distributing that kind of way? It's just kind of weird to go in from both sides into one spot. And then on the next distribution, the negative is multiplying here, so it's positive 3. 2r is multiplying here, so we'll get a plus 6r. Now there's another simplification. We have like terms that cancel off. The 2r cubes are just gone. So there they are, gone. We could add these up to get a 12r times 6 will give us 72r altogether. So here's finally our result. 72r times r squared minus 3 to the power 5 divide by r squared plus 3 to the power of 7. Finally, that's the function that we're going for, the derivative of this admittedly kind of a mess function right here. Any questions at all, folks, on getting through this one? Okay, to me, I think these are again, kind of the tougher questions in this section's homework. Anytime you use a chain rule, also try to identify, is there a product rule coming up? Is there a quotient rule coming up? If you look before you leap, you'll spend much less time on the question trying to go back and fix other rules we might have missed on them. And it looks like we have a good, strong about 11-ish minutes. So I'll leave it up to the class. Should we try a question like this one, or would you all like to try the application? Awesome, let's give this application a try. Thanks for being the lead on this question for the day. So this application is kind of tricky. What makes it tricky is we don't have X's and Y's, and we should expect it in an applied problem like this. All the variables now take on meaning and different letters. So it says here, the speed S of blood, that is R centimeters from the center of an artery, is given by that function. So if we have a blood platelet right here by the red dot, its speed is dictated by all of this stuff right here, how far away it is from the artery wall and so on. The arrows are indicating that at this midline, the speed should be the fastest. As you get up here, where your plaque might build, if you're having other issues, it's a little bit slower. So it says here, C is constant. R is the radius of the artery. S is measured in centimeters per second. And now let's go to the next. But anytime they tell you something is constant, whether they're specific, like where we highlighted, or if we have to infer it, it's a good idea to write it down. So C is constant. Now it says next, suppose a drug is administered and the artery begins to dilate. I believe dilate means contract, or does it mean open up? Oh, it's opening up, gotcha. So some kind of steroid is opening up the artery at a rate of dr dt. It says at a constant distance r, find the rate at which s changes with respect to t, where the constant c in the original function is defined. R, the radius of the whole artery, it's defined to be this, which means R is also constant. Or hang on, I think I made a mistake there. At a constant distance, find the rate at which S changes with respect to time. The artery begins to dilate, that's uppercase R. I don't believe that's constant. R is changing, it's getting bigger and bigger. So that was definitely a mistake. That's just a value we're going to plug in at the end of our answer. Let's see here. Something else is definitely constant. They said here at a constant distance R. So that's our second constant, lowercase r, not uppercase. So that one's constant. So we're assuming that our blood platelet that we're tracking is right here. And now distance r is not going to change at all. We just want to know how fast is that thing going. So we have two constants here and here. Here's the big thing that we want to determine about this. This implies that S is the dependent variable. And uppercase R is the independent variable. Think of your dependent variable like a y in a problem, and your independent variable like the x in the problem. So it looks funky, but that would be like a y equals a constant times x squared minus another constant squared is what we're dealing with. So let's grab that function, s equals, that constant there is kind of annoying, but you could just distribute it through and get c times r squared minus lowercase r squared. Now let's take a look at the derivative they asked us to calculate. They said, find the rate at which s changes with respect to t. Let's give that a special color. That's the question. And the question, if we use Leibniz notation, this is the great time for it. Applied problems go fantastic with Leibniz notation. From here, we would write ds dt. So that's the derivative that we'll calculate. Yes, go ahead.
So minus the are.
Oh, that was my mistake right there. Thanks for spotting that. It should have went, like you said, here to here and here to here. So minus c lowercase r squared. Thanks for spotting that. Other questions or comments at the moment? Yeah, go ahead. Because they said respect to t for time on this one. But again, that's kind of weird, right? Because we do have things like, well, a dr dt here, dr dt here. But if s, sorry, I'm pointing at my screen, if r is the independent variable, you would more rather like to have done, say, ds dr, right? That's the more natural derivative. But if they're asking you to do a different variable t, that's a telltale sign. It's because this one is a chain rule kind of problem. So here's how it goes. We're differentiating the function s in black right up above. It's going to turn into, first, c is a constant. So this is the constant multiple rule. C copies in. Next, r squared. That one is a function composition. There's two functions here. There's r, this one is the inner function. And then there's the power 2, that one's the outer function. So r is truly a function that depends on time. We see that when I say dr dt. So if we differentiate this function, here's how it goes. I'll take the derivative of the outer, 2 comes down. The new power is a 1. And then we take the derivative of the inner. This would be dr dt. So we have dr dt as the end derivative right here at this location. Well, we have dr dt supplied right here. And so now that's pretty much the chain rule altogether. Does that make sense to folks at this stage? Oh, I think I did have one small omission. Let me put it right here. When we did the outer function, it was 2 power of 1, and then multiplied by the derivative, dr dt. And the r right here is what should have copied in. Let me highlight that in yellow. That was my omission right there. And that's a power 1, just showing what happened with the chain rule. It's not a derivative. It would have to be kind of angled a little bit more for that to be a prime. So we have it, folks. That's the real derivative. But it's said to find the rate at which s changes the speed with respect to time, or the constant c given here, the radius of the actual, this was a blood vessel given here, and when dr dt is given to be this value, 10 to the power of -5. So it turns into a substitution problem. We'll put in for c, 1.76 times 10 to the power 5. Then we'll double 2 times r. R had to be 1.2 times 10 to the power of -2. We'll multiply that by dr dt. Here it is. That one's 10 to the power of -5. One thing I didn't have time for, which is kind of a shame, is when you're doing this, it's also a good idea to put in the actual units of everything you're dealing with, just to make sure your dimensional analysis is actually correct. You're really getting the right unit you're expecting. Didn't quite have time for that, so I just dropped it all inside. And if you crank all this out, we find that ds dt comes out. I put this in a calculator and got 0.04224 centimeters per second. And this would be centimeters per second squared, which is already kind of a weird concept. If this was the speed and we differentiate what's the speed, we're getting an acceleration right here. And so that's what we get as the value here. So the rate of change of the speed is acceleration, and that's why there's a power 2 on the seconds on that denominator there. Well, any questions, folks, on running through this application? Yeah, go ahead.
So why didn't you do the do anything with the negative dr lowercase r squared?
Oh, sorry, I should have mentioned that, but I think I was just rushing through it. It's because this stuff right here are all effectively constants. So upon differentiating, it just vanished entirely. Thanks for mentioning that part. That was the whole reason of writing this stuff in there right there. Other questions at the moment? Okay, And same reason for why this C copied in right here unchanged, only because it was a constant multiplying. Well, I think that's pretty much all we have time for today. Any last questions at all, folks, before we call tonight? Okay. In my opinion, this application is really pretty dang tough. But the good news is it's like a preview. We've done 2 of them now in class. This is all just trying to get us prepared for once we go into chapter 4 and the problems start to look more and more like this. It's not forever for the rest of the course, but we'll see these kinds of things in that application section. Well, have a great night, folks, and I'll see you all in Thursday's class. When we come back, we're implicit differentiation. The punchline is it's still the chain rule. It just looks weird.
2.7, assignment 2, Brian, and the last 3 questions are the same.
Oh, gotcha.
I should demo tonight, that works for you.
Yeah, that would be perfect. All right, thanks so much.
Yes, thank you for your patience.
Yeah, no worries. I mean, it's tough joining the class kind of late like that, so no worries. Questions?
I just, so this would be okay, right?
Or this is an answer? Yeah, I'm totally great with that.
Okay.
Awesome.
This is just the homework for it.
Okay, thank you.
Thank you so much.
You bet.
Silly question. So you're differentiating r squared minus 3 over r squared plus 3. Why couldn't we just cancel out r and then that would be simplified to -1?
Oh, the trouble is if we say, I shouldn't draw on student paper. Let me put it on the chalkboard, or if you don't mind.
Yeah.
If we did divide this r squared right here, we would get a 1 minus 3 over r squared. Then that would turn into a 1 plus the 3 over r squared like that. So that's the trouble is if we cancel 1 r squared, we're dividing by r squared. And so the whole thing has to get divided by r squared.
Okay.
Unfortunately, yeah.
I
If
see
it
what
was
you're
say multiplying like 3 times r squared divided by like 9 times r cubed, then you could do those kind of cancellations. But the pluses and minuses, they always just mess up algebra essentially.
Oh, thank you.
Yep, you betcha.
I'm just wondering if I even had more question on doing this stuff.
Sure, say like on 27.
Well, I already got this one right. I know I did this one. I'm more about
Oh,
these two
gotcha.
and this one.
So,
I already went through, I don't know if it's right there. I'm not sure if it's correct, but I had to write on space. I had to kind of squeeze it in.
gotcha. So we're looking at problem 13 here.
Yes, but I want to know if this is even, this is correct, because this is like 24 U3 plus.
So we're looking at 12 then. So first for 12, 6u4 minus, or 6b power 4 minus 5b over b plus 1.
I think it's U.
Or u, gotcha. So it's definitely quotient rule. And you've got here, minus 5, that looks good. If you do the derivative right here, you probably don't want to put that prime symbol. That's just a tiny comment. Because it's saying to differentiate again, essentially.
Oh, I'm just leaving it there because I just basically, I left it there because it's like, oh, I just derivative with this. And because I had the amount of space, I just reused the line again.
Yeah, that makes a lot of sense, yeah. Then copy this down below squared. This copies in, and the derivative should be 1, yeah. So
basically that would be the answer right there.
Yeah, that looks great.
And this one is basically, I just do with this up here, what I did there.
It's exactly, yeah, same kind of thing, just slightly different functions.
Basically, this guy's gonna add that like thought this to this T right here.
It'll distribute through, yeah, and get
So
5.
all of this is just gonna be plus 5 or times 5 here.
Mhm.
And along with this one, which is gonna be T5, so.
Yeah, I think on this problem, you'll get a little bit of a simplification there.
Okay, yeah, I see where this is gonna be going.
Cool, cool.
Yeah, because I was like worried about it. I was like, I don't know if I'm doing this right. I
Yeah.
just want to have this one set up like this. And I think this is how it's supposed to look like.
This one is a little bit weird because the back of the book solution, someone took like 12 steps in algebra that they didn't even have to take. This one's just a product rule. After you set up the product rule and differentiate, you can leave your answer in that form.
So basically, I can just take this T and turn it into a square and I'll be done, basically.
Turn this T right here,
That's square.
it'd be a power 1/2 right here.
Yeah, which is like this right here.
Yeah, you still have to go through the product rule for this one,
So basically,
but you don't have to simplify it to their form.
so would I have to just take this and distribute it onto this and I'll be just basically done?
Oh, you'd still have to differentiate if you distributed.
So I would have to differentiate this and this and it would be basically done. Right?
Well, there's 2 ways. If you're gonna distribute first, then you'd still have to use a product rule.
Okay, I
You
think I
don't
just need to show
distribute.
this because I'm not understanding.
Yeah, let's put it on the board. It goes I already forgot. How does it go?
T plus P E to the power of T. Then it's the square root.
Gotcha.
Square root.
So you mentioned two strategies. Did you want to distribute first or just differentiate as it stands?
So do the fastest way because I work best with fastest way because it just,
I hear you on
it's
that.
something I like to do because I like to cut through problems faster. So that way, because it stresses, so I struggle with test anxiety at normal.
Mhm.
So I always take the shortest route because the less time I'm doing the test, the less pressure I'm under.
Makes
Yes, I
sense, yeah. Gotcha.
So I always take the fastest route. So.
Let's go for the fastest route then. So I'm gonna take all of this. Prime, just to say I'm differentiating that. Because of this right here, it's a product rule. So we'll go. Like that to start out. Then T plus two to the T goes in those first locations. So T plus two to the T. You know, this derivative is not too bad. Do you see what it would be just by
Well, the first one,
visualizing it?
one T is basically just turning non-existent and then it'd be two.
Well, this would turn into a one.
Oh, yeah, because it still then exists. It just
Yeah,
becomes one.
yeah, the T kind of vanishes, becomes a constant. I see what you mean, yeah. How about for this part?
You would put the T in instead of between the two and then it would be two T.
Close, but this one's a little bit different. Because it's an exponential function, e to the T, when you differentiate this one, just becomes itself, e to the T.
So basically it just doesn't change.
Doesn't change, yeah. You'll get one plus two e to the T on that one.
Basically, it's just ignore it.
Exactly,
It's
yeah.
fine.
Just like the world's best function, really, yeah. Didn't matter if you differentiate it or not, it's still itself.
And then you're gonna have to distribute it onto square root of T.
Exactly. So that goes there unaffected. T plus two e to the T goes here unaffected. And here I write this T as power one half, because we do affect it, we're differentiating that one.
Okay,
So that's our setup for this kind of problem.
now, I'm not sure how I'm supposed to do this with the square root. Because the only thing I can really think of is the one times a square root would just be square root, because the one can't change anything.
Are you referring to this derivative right here?
No,
Or-
because this became a one.
Yeah.
It will not affect this because it cannot affect it. One cannot change anything but a times derivative. Because one cannot change anything.
So yeah, if you multiply through, you're just gonna get root T here.
And then you're gonna get two, leave it be two, root T.
Well, it'd be, when we multiply here, there'll be two root T, but we still copy the e to the T.
And basically you just throw that in on the outside of it then.
You could put it anywhere you'd like. You could put it, say, two e to the T root T. That's all completely up to you, pretty much.
Basically it doesn't matter as long as it's T.
Just gotta be there, yeah.
And then this one would just be that, which would be just basically one times one half.
Or this one right here is a derivative?
Yeah, because you have to throw that onto that, and that would be one times one half would be basically. I believe it would be. Would be technically. The one half.
Yeah, exactly. But you're saying when the one half comes down here,
Mhm.
you would get T power one half prime. You'll get a one half here. So what would your next one be for T?
It would be. Well, it would be negative, or you go ahead and do it, because you have to minus it by two, so it would be negative one half.
Yeah, good call. So that's what's gonna go in this location, and then like you said, it distributes into that group there.
So basically, that would just be. Like, basically, put that right there, because we plus that, we basically, well, for one, that positive, could actually turn to a positive and be just one. Because there's reverse the negative, which is going to.
Yeah,
and this
absolutely.
side is Positive, and then because the full exponent is, then it would turn to positive.
It turned into a positive one half for exponent, exactly. So back to square root essentially.
And this would basically just be, basically what that.
Yeah,
And that's just, that's it.
it is, yeah. And like I said, your answer, if you compared it to the back of the book, they look different, they're equivalent algebraically, But I'm not worried about you taking like 13 steps in algebra to make your answers look right. As long as you get the derivatives correct, that's what I'm looking for.
I need to represent something.
Yeah, I know what you mean.